Okay. Record start. Okay, let's start. So hello everyone. Today I will introduce you guys some Kolmogorov-Arnold network. This is a new topic.
Okay or no?
Do we need to click OK? Yeah, let's click OK if so. Okay.
Now let's start.
Okay. Now it's start. Okay. Hello everyone. And today let's try to discuss some idea on the Kolmogorov-Arnold network that is called CAN. That is a new topic that is developed by MIT in this April. It's MIT, not a vegetable university, Yeah. Yeah, it's MIT. Yes. It's it's a new topic. Yesterday I talked with Professor Shriut. As my understanding, this is more like machine learning. Before machine learning can only do summation, right? Because what they are doing is sum all of the things together. But now what we want to machine learning try to learn something called the solve a function. I think that's the huge improvement. That's why I want to introduce you guys on this one. Let's start. First, I want to thanks to everybody. This presentation is a combination of the internet content. Thanks to every authors listed below. And also I searched a lot of works of others because it is too long, so I don't have enough space to list everyone. But thanks to every content showed on the internet. And also thanks for the ChatGPT, because with their help, I can read the content and understand it better and faster. Also, we thanks the support from Synchro Media Lab and Professor Shriut. Yeah, let's dive to the details. First, I want to give you some outline of this presentation. So there would be 4 sections, but there are 2 main parts. One is, one is the problem of multi-layer perceptron. That is what is the problem now we have, and then we will talk about how do we solve it. How do we solve it? That is the Kolmogorov-Arnold network. I will start from beginning. Like I said, I want to, it is an improvement from 1+1 baby to a high school student who can solve the function. So I will start from high school until how do we get the Kolmogorov-Arnold network. So, and then I will talk about the performance, and then I will talk about the future research directions, because this is a new theory and a new method. So I think it is still premature. So I think we will have a lot of stuff to do for our later research. So that is the outline of my topic. So let's talk about what is the problem of multi-layer perceptron. The first problem is the curse of dimensionality. That is, the common problem for supervised learning and reinforcement learning. So what is the curse of dimensionality? The curse of dimensionality is a problem with the relationship between dimensionality and volume. Let me give you an example. Suppose here, if our, like in our reinforcement learning, if our state action space is only have 10 points in 1D array, that is only 10 points, right? However, if we extend this work into 2D array, that becomes 10 to the power 2, that is 100. That means the space is 100. After it, welcome. After it, if we increase into 3D, the space become to 1000. If we turn to 10 dimension, that will be 10 to the power 10. That is a huge amount. What is the problem? Now we know the machine learning require a lot of data. Why do we need such a lot of data? Because when the complexity, when the space is really large, we have to make sure the space is not biased, or it is not really concentrated in one area. For other place, it's empty, or it's only few points. In this case, we can train some points only in the centralized or focus area. However, for some empty space, we don't know what will happen. But in test set, this data will come. That will become some issue, right? That is a really, really important issue, because with the more and more complexity, especially for large language model, our income would become infinity, and outcome is a generative model. So the outcome is also almost infinity. Infinity times infinity become again infinity, but the data we have is limited. So definitely we will have some space. We cannot say we don't have any example, but it can be asked, or we can meet during our test or during our practical use, right? In this way, we cannot get the really good solution in practice. This is called the curse of dimensionality. So if we talk it theoretically, that means the sparsity of data occurs when we move into higher dimension. Because when we move in higher dimension, no matter how dense your data is, when we increase the dimension, it would become sparse than before. With more and more, it becomes sparse, and then the volume of the space represented grows so quickly that data cannot keep up, thus becomes sparse, and that will cause some problem. This is the Bellman theory, not the Bellman equation we mentioned before. This is the Bellman theory introduced by Bellman in 1957. This is one problem of multi-layer perceptron. Because multi-layer perceptron can only train in its, its dimension. If we increase it, they cannot do nothing. And also it is not interpretable. That means it cannot explain. If we don't know how it happens, of course we don't know how do we solve it when we increase the dimensionality. That is the first problem of multi-layer perceptron. And there's another important issue, that is neuroscaling law. Neuroscaling law refers to the phenomenon that tests the laws x beta and exponential law, power law relationship as a factor such as the model size, data, and calculations increase. That means, I'd like to, explain this one is for every machine learning model now we meet, they always have some, comfortable space. What do I mean comfortable space? That means in this space, our accuracy is high and the computational complexity is not high, and everything is perfect. That is a trade-off problem. Now what we are trying to do is find this comfortable space, and that is what we are using for machine learning in supervised learning or reinforcement learning, right? However, if we change the model, like the model size, or we change the data, maybe we have more data, or even we increase the dimension, we will go out from the comfortable area. That means, the reinforcement learning cannot perform well like before. That would be a huge problem, because now for machine learning or reinforcement learning, anything is trained for specific task, right? That means, you train your model, you have to know what exactly your task is. But the word, it is voracious. That means it's always changing. If we train every model with this comfortable area, that would be huge work. That's why there are so many papers annually, because for each specific field, they will have some comfortable field, and maybe they have some comfortable, method or solution. So there are so many papers. But the people the people resources are finite. That means they are limited. We cannot make it always, train for any new things. So that comes to the problem that neuroscaling laws. And when we consider the changing things, the environment is also changed. For example, for our reinforcement learning, maybe recent days, the Markov decision process is maybe in one probability, and the other days maybe it go in other ways. That means the probability is changing with the environment. Also for other machine learning methods, like the image or large language model, people's preference are changing, right? Because maybe today, maybe before, maybe there are some important topic like TikTok. Now maybe Snapchat is coming. So people watching TikTok also watching Snapchat, but they have different preference. For currently, what we have to do is train for in the comfortable area, right? So that's not only the the neuroscale law problem, that also comes to another problem that is a continual learning problem. I will explain it later. And there's another issue, that is the representation. We know, multi-layer perceptron, they use the summation. They use, something plus something plus something. Of course, we can get all of the, functions as we want. It depends on how deep your neural network is. If you make it infinity, theoretically, you can represent all of the functions. But if the neural network is really, really that deep, there would be a problem. That is, gradient explosion or gradient vanish. The gradient vanish is because it's too deep. The gradient is too small. One small number like 0.01, 0.01 times 0.01 times 0.01, it becomes smaller and smaller until 0. Or gradient explosion, at that time when it is too deeper, maybe 1.1, if you maybe 1,000 layer, 1.1 to the power 1,000, it's a huge number. Reinforced gradient descent maybe cannot handle it. That comes to the gradient vanish or gradient explosion problem, right? Make the neural network deeper and deeper is not a really good solution because, it cannot be trainable. And also for our machine, the memory, I mean, like the graphic cards or, the computer's memory is limited. We cannot make it deeper and deeper because for each time for back propagation, we have to, suppose we use the atom, we have to store the previous number and also gradient and also the intermittent variables, middle variables. So that would be huge. That is the increase, exponentially. So we can
minimize the batch.
Yes, that's why we minimize the batch. But even though there are some complex function, we really need some, some high dimension, deeper things to represent. But now we need to find some ways to represent efficiently. So that comes to the problem that is, multi-layer perceptron. It is hard to represent, some complex function. For example, I give an example that is the Basel function. Basel function is the useful function to represent, the regular life things in a lot. This is second order. For this one, we need a really deep multi-layer perceptron to represent it, and then maybe the accuracy is not higher enough. So that is another problem. Multi-layer perceptron is hard to represent the real world, what it looks like. And another reason is the interpretability. What is this? Now in our multi-layer perceptron, we know how to train our neural network, how to train. First, the problem comes from, why do we need activation function? Why do we need it? Because we want some nonlinear, nonlinear reality. If we don't do this, every line had to be a straight line. It can go to other direction, but everywhere it has to be a straight line. But in our regular life, it is hard. In order to, also, there are another issue that is if so, the gradient will keep unchanged. Yes, so we cannot update it and make it better. So in order to solve this problem in multi-layer perceptron or in machine learning, what we do is we introduce something called activation function. With this help of activation function, because for each place, there would be some curve. This curve will help us to separate, different variables easily. And also with this curve, we can improve our model by gradient descent. That is, the motivation of gradient descent. However, how this curve affects our model, we don't know. What we are trying to do is now is in machine learning is like what we did in reinforcement learning, trial and error. We trial it, see whether it increases or not. If it increases, that means the direction is correct. It goes into the gradient descent that go to the lost descent action, and then the model increase. Right, but as for how this model affected the real with the machine learning, how it works to affect the practical life, we don't know.
Yeah, it's like a black box.
Yeah, it's like a black box. Yeah. With this black box, we cannot update it. That's why there are a lot of works. Maybe they try to do it. It cannot improve our performance. Why? Because we don't know how the machine learning, the model affects the final result. What we are trying to do more or less like a try it. If it is increase, yeah, this is a good method. If it is not a good, if we not increase, maybe it decrease. We say maybe this method is not good. So that is another problem. Because of this, so we can the activation function we cannot adjust it because we don't know what happens. So how do we adjust it?
But when you use activation function, we have some reasons. For example, when you use ReLU, like we take max between 0 and x. So we want to focus on some features than others. And we have reasons to use this activation function.
Yeah.
So in this case, why we need to change or to adjust this?
Yeah, adjust. How do we adjust it for multi-layer perceptron?
My question is why.
If okay, that is a good question.
Now use the
Yeah, okay. Yeah, that's a good question.
Why I need to adjust this?
Okay, because you know, well, now we have some activation function, but as for how perfect it is, we don't know, right? So what we want to do is adjust it and then see whether it's perfect or not. We want to get the, you know, the most fine-tune. Yeah.
Fit like your use case and problem.
Yeah.
Yeah.
Depends on the
on the
nature
pro,
of the
yeah.
datasets. Yeah. Some datasets, if you use only ReLU, it might load some information. Because any variation less than 0,
It's like that.
that's why you lose some critical information. But if there are some variation of ReLU, little period.
Okay, everything is good here? Okay, yeah, let's continue. Another issue is what I explained to you. Now what we are trying to do is in some comfortable area. For example, now we have a reinforcement learning model. We have different phases. At phase 1, the comfortable area is in the first peak. For currently, what we do is train for the first peak. Like this one, we train for the first peak. And for others, I don't care because it's not in my comfortable area, so I don't care. Yeah, and for phase 2, we also do it separately. For phase 3, we do it again separately. As for how this works in other region, we don't care. But our life, you don't know when the phase 1 will be changed to phase 2. And you don't know the existence of phase 1 and phase 2. Yeah. You don't know anything. I come to how do we solve this issue? Yeah, that is another problem of multi-layer perceptron because it is simply sum them together. Yeah. So that is the problem currently we have. So let's come to, you know, the solution is Kolmogorov-Arnold network. That is the CAN. Okay, so let me first give you briefly idea what it is, and then how this works, solve this issue, and then I will start from beginning, from drawing a line, drawing a function, until how do we get this solution. So first, this is our multi-layer perceptron to use the universal approximation theory. To use this theory, the formula would be fx is approximate equal, because what we are trying to do is gradient descent to get the loss is the minimum. So that is the approximate equal. Approximate equal to the the activation function times the wi, that is our weight, plus the offset, that is the b. That is what we do in formula. But is there a way that we simply use some function and the input is a function, and then with a different layer, it is the function. We always go in function ways. In this way, because for this one is simply summation. If it is a function, if we can get a function like this one, this is strictly equal, right? And with this one, we can, with this solution, we can look at the previous problem because it is a function. It is a function, so in everywhere, it is always have a output, right? It is a summation of some function. So in every space, there would be some solution. So there's no the curse of dimension problem because it's a function, right? And another issue is, let me see what I introduced, another thing. That is, neural scale law, because, now we don't have comfortable space, because what we are trying to get is the real function of the output. So it is a function that is for all of the spaces. So it shouldn't be have previous problem, right? And also for the interpretability, because we already know the function, we know how do we adjust the activation function, right? Because we already know the function, we just see where it is perfect, because we already know the function, right? And another issue is
Oh, it's okay. We can discuss it later.
Yeah. Another issue is the continual learning, because for continual learning, in different spaces, what we know is in each phase, what it can represent. What we can do is we can write in different phase. We can have some time variable and then train this variable. So, maybe you will ask question, why don't we do in MLP, right? Why not we put the phase into extra variable? That comes to extra issue. That is previously we mentioned the curse of dimensionality, because you increase the space. That's called the extra curse of dimensionality. So, Kolmogorov-Arnold network can solve these things better, because it has less weight. And another thing is because for each thing it is simply the function of a previous one. So because it's a function and functions of a function and functions of a function, the complexity would be less. Because see here, for each node, we should get the weight and then get the weighted sum, all of the weighted sum of previous layer. But this time it's a function of function. We don't consider what other neurons output for previous layer, right? So this one, the complexity would be less. So that is the idea for Kolmogorov-Arnold network. As for how it works, let's start from beginning. Okay, so let's first talk about something that is Bezier curves. I think this one everybody should understand it, because that is the high school content. But I will first try to give a summary on it. The Bezier curve is a parametric curve, which means that all of the coordinates of the curve depends on an independent variable t. The t is between 0 and 1. I think in middle school or high school, we learn if we want to get a straight line, how do we get it? We can get the slope and 1 point, or we can get 2 points and then get this straight line, right? That is the first order of a Bezier curve. That means any straight line, it can represent by P0, that is the one vector, that means the one direction, that is the 1 point. Yeah, and P1 is another point. We can give it as P0 plus T, P1 minus P0. That means 1 minus T times P0 plus P1. That is the first order. That is we already know from our middle school. Now, what if I give you 3 points? Do you think what can we get?
Sorry, what's T here?
Sorry?
What's T?
D? Where is D?
T. T.
Sorry.
Direction to some slope, the slope T.
Oh, you mean T, right?
T, the letter T.
Yeah, the letter T is it's not slope. I think it is because it is what is the percentage of this point, the vector. You can what we can.
For example, T equals 0.
Mhm.
So it
T,
can
yeah.
be a straight line.
Uh-huh.
So T
Yeah.
is like a degree, like
Yes.
because line is like the first element of this equation. No?
Yeah. Okay. Okay. If we are given 3 points, what can we get? Any idea?
If what?
If we are given 3 points, what can we get?
Curve.
If we get 3 points, because 2 points we can confirm a line, right?
Yeah, 3.
Have 3 lines, 3 points.
3, 4, 2.
It depends. If it's Euclidean.
It can be a line, but it can be a curve, right?
Yeah, it can be a
But
curve.
before it, let's first define what is a curve. Any idea what is a curve? Let's see. Yeah. I mean, do you think this is a curve? Yeah, this looks like a curve. Yeah, but yeah, this is a curve, right? But what if this one? This one is a curve. No.
I mean, we discussed it last time. It's about for example, at this point, it's not differentiable. Yeah, convex.
No, that is not convex. I mean a curve. It can be convex or concave. I mean, for curve, that means it's close to the definition of convex. Because in convex, what we say is for any point from this curve, we select 2 points. That is, there it can be represented as PT is less than or equal to the the 1 minus t times yeah.
So there, like it's gonna be differentiable on all points.
Exactly. Yes, that is for every point, it's differentiable, and also the tangent should be, from the left direction, you get the tangent, and from the right direction, you get the tangent. They should be, consecutive.
Okay.
No, that's why this one is not, because from this direction, you got the tangent. This direction, you got the tangent. They are different. Okay.
You mean continuous?
Yeah, continuous. Yes. So that is the curve. So that comes back to our question. If we are given 3 points, what can we get? We can get a curve or straight line. Here we can consider straight line as a special curve. Yeah. Because as we defined, from each direction, we will get a curve. We will get the tangent is the same. For a straight line, it is follow this rule, right? From this way or this direction, they have the same curve. So that is the idea, that if we are getting 3 points, we will get we will get a curve, right? As for mathematically, how do we get this curve? That is qt, q0 t is equal to 1 minus t times p0, and then plus t p1. That is the one line, right? And we have another line that is q1 is equal 1 minus t times p1 plus t times p2, right? And then if we take this one back to here, we will get a second order. That's the curve. Yes, that is the curve, right? So if we can use this Bezier curve, as a function to replace the summation, now what we have to determine only where is the points and what is the t, right? Theoretically, if we increase the order, it can represent any function. And it is more efficient because it's a curve plus curve. It's better than, sum. Yes, it is better than universal approximation summation, right? Okay. But the problem still exists. What if n is equal to 1000? Yeah, first by the curve, if we can write it in in an equation that is bt is equal to from from 0 to n, that is the combination of n of I 1 minus t times to the power n minus I times t to the power I times the pi for each line.
So we want to identify the t.
Sorry?
We want to learn the value of t.
Yes, if we want to determine a function, we have to learn the t. If we are given some points, right? We can learn the t. But this way is not good, because this one would make the neural network even complex. For example, if here I give you 1000, n is equal to 1000, that would be huge space, because the combination of, suppose the degree is 3, 1000 takes 3, that is a really large number. But theoretically, this one would have a better representation ability than the multilayer perceptron, right? So is there any way to make it better? Yes, we have. Let's come to another thing that is called the B-spline line. Instead of get the combination of all lines, what we do this time is we will make it into different pieces. We will make the curve, cut the curve into different spaces. For each space, we only determine 3 points or 5 points. It depends. In this way, like from 1 to 0 to 1, I have 3 points. You only determine the points from 0 to 1. And then from 1 to 2, you only consider the points between them, maybe 2 or 3. You determine this point. And then in this way, the complexity would be decreased a lot, right? Yes. So let's come to the idea that is this technology. This one is called the B-spline line. Okay, so what we can see theoretically is the k degree curve. What is the degree? That is what we say, how many determining points minus 1. For example, before we said second 3 points, we can got a second order. That is the second degree 2, right? And then because the highest order is 2. Is degree 2. Here we can see, the k degree is one line curve that is defined by n control points, will consist of n minus k border curves. For this one, you got the idea?
No.
So the k degree here is determine derivatives.
Sorry?
The derivatives, the degree of derivatives or what?
That means the k degree represent what is the highest order of t we mentioned before. For example, I will explain to you later. Let me first answer his question because later it's they are connective. Yeah. For example, here, what is the highest order of t? This one, 2, right? With 2 t to the power. So this is the second order. So the degree is 2. How about this one? This is 1. Yeah. So what is the k? The k is the power of the highest power number of t. Yes, this is k degree. And then your question is sorry.
Yeah, it's about like on the figure if you want.
Okay. For the figure, suppose now the k is 2. That means for each space we need 3 points to determine this curve, right? If so, how many curves we have? We can calculate it. That is the 1. This is the 3. 1, 2, 3, 4. 4, right? And then we have 4 borders, and then the order is 2, and then totally how many points we have? Determine points. Totally how many the control point the point we have.
6.
Yeah, 6 because 6 points because you can see this 3 it determines 1 curve, and this 3 it determines 1 curve. Yeah. So overall it is 6 minus 2 is equal to 4. You got the idea why it is n minus k? Okay. So any question? Okay. So in this way, the complexity of the decreases sharply. Also at the same time, I still can represent my function, right? So this is maybe under current case, this is a good solution, right? So that
but if you have huge value of n, for example,
even
1,000.
For example, you still have 1,000.
So you have around 1,000 k.
Yeah,
What,
is this only 1,000? Yes, compared with this one, if this number, if n is equal to 1,000, it's a huge number. Because if you have 1,000 points, this one would be better than multi-layer perceptron. Because if you have 1,000 neural, it is 1 layer 1,000, another layer 1,000. That is 1,000 times 1,000. That is huge, right? So this way, it makes the complexity much lower, right? Okay. So let's talk about the Kolmogorov-Arnold representation theory. For this theory, what we see is if f is a multivariable function on a bounded area domain, then it can be written as a finite composition of a continuous function of a single variable and the binary operation of addition. More specifically, we can see for a smooth f, we can say it is a summation of the of a function, and then the function of the summation of previous functions, and then we sum them together. That is the output. That means this one can represent anything we have, right? So that is the Kolmogorov-Arnold representation theorem. Let's compare with the universal approximation theory. For this one, I think you guys should be familiar with what we have is O equal to the output of a previous layer, and again previous layer. Yeah. Sorry.
This one, perceptron, like
Yeah, this is multi-layer perceptron. Yeah, the theory behind it is called the universal approximation theory. So, of course, now the advantage is clear, right?
Yeah.
Okay. Yeah, let's see what the Kolmogorov-Arnold network it is. Suppose we have an input, and then we will have a different file. What is the different file? That is different, the B spline line. And then you will train different curves. And then what you have to determine is what is the stop point, what is the control point, and then what is the T, right? You control this thing and make the combination of them, you add them together, and then you will generate the output. That is the one layer. We can make it deeper and deeper, but even deeper and deeper, if we find some function, we know what the function looks like. So when we want to adjust it, we know the function, what is the distribution function, we can easily adjust it. And then in some unknown space, I still know the function, so there's no such issue. There's no curse of dimensionality issue, right? Yeah. So that is the Kolmogorov-Arnold network. It looks like, I think until here, you guys will be familiar. Yeah. So let's compare them again. So for multi-layer perceptron, to use the universal approximation theory, so it is approximation. This one is use Kolmogorov-Arnold representation theory. It is strictly equal, and the complexity is better.
But here, like, okay, for the multi-layer perceptron, we have like an approximation, right, for the f of x.
Yeah.
So it's an approximation, but here, like, you got like f of x equal.
Yeah, equal.
But if you have like a continual learning, for example, dimension like still moving, it's still changing.
Well, you know the function. If you know the function, you know what is the distribution in every space.
Yeah, but do you know like every function? You know all the functions or what?
Yeah, you know all. Yeah, you know all of the functions. That is what we are trying to do. That means you use this function like a B spline function to represent it.
But it's not the exact function because
yeah, it's not an exact function. It's still some approximation function, but it can tell you, in which function how many percentage it represent for what, and this in this way it's interpretable. And then if you want to adjust it, you know in which space to adjust it, right? Yeah. So
what's the type of these functions?
B spline function. Yeah, we introduced here. Yeah, this function.
Okay, but how, like you say, it's interpretable?
Yeah, because we know how it is, what is the distribution and what is the what is the variable. I mean, it's spell variable in different spaces. You know what is the contribution of each each function, and then based on this one you can explain it, right? Because you can explain like what is the percentage of this variable and this function, what's the percentage it represents, and it affects your result. And in this way, it is interpretable because you can adjust it.
How we can initialize the model like randomly, for example, in the weights at the beginning. We just put random values.
Yes, that is a good question. Yeah, I think we can go through an example. You will see what will happen.
Yeah, regarding the last question, but the function itself, I mean, like it needs to be interpretable, no?
No.
I don't care if you told me like the first function is responsible for this.
Yeah, for that one it is impossible. But I mean, it can only tell you.
Narrow down.
Narrow down. Yeah, as you believe 100%.
So like function was responsible below.
Yeah, it is hard. Yes.
Yeah.
And for how this one represent, the author of this paper gave us an example. Although this is not a the Khan network, but it gives us an example how it is interpretable. That is this one. Suppose we are trying to get it. We are given x and y. What we are trying to export is the exponential sign pi x plus y square, and then we have different functions. We have different functions like sine square or something. This is not we use in Kolmogorov-Arnold network, but they just give us an example to see how it is interpretable. That means, for example, if you get the sine, and then here you get the square, and then you sum them together. And then again, here you select another function like the exponential, and then you will get the result. That means how it interpretable, because you know from beginning how you do the the transformation, and then you arrive the result. Right?
But in reality, we don't know this function.
Yeah.
We have data of insurance.
Yeah.
Power of
After you
and age of people, and we try to train.
you don't know that one, but after you train, you will know this one. You can see what is stored in your neuron, right? So you know that one, and then you know how they combine together and get the result. So that's called the interpretability. In multi-layer perceptron, we only know some way to plus them together, you got the result. As for how, you don't know. Yeah. So that's why this is interpretable.
So at the end, we can know the function. We can know.
Yeah, we can know the
mathematical function.
Yeah, mathematical. How mathematically is from the beginning we can arrive the result.
And that's the difference between interpretability and explainability.
Right.
Because in interpretability, like we can know which part of the function is responsible for this, like production of this, approximation. While like in explainability, it's like you need to explain it in human terms.
Yeah.
So I don't know if this method we can like work with like image or computer vision.
No.
I don't know how this.
You tried it?
But you cannot generalize. If it doesn't work with you,
Okay.
it doesn't mean
It wasn't immense, but I tried it with a bit more.
Okay, so there is an opportunity to
improve.
Yeah.
I think this more or less, tell us, what is the
If it's still new, you can like
yeah.
later
Maybe.
on you can add, like,
Because everything is
It
implemented.
gives a little bit less like performance compared to NLP.
Yeah, because this one is still in primitive, work. There are some use like a time series that show it is really good.
Forecasting time series.
Yeah, forecasting. There is also already some work, but I have to say everything is still in primitive, not like multi-layer perceptron. We know gradient descent to update it. We know how exactly it used. For this one, I have to say everything is in primitive, so we still have a lot of stuff to do. I will talk about this issue later. Yeah. So let's look at the performance. So this is the result, the author gives to us. The Kn represents the replace the multi-layer perceptron. And then let's see the second order Bessel. That is a hard question, right? If we use the Kahn network, that what we can see, it is 1.49 times 10 to the power -5. But if we use MLP, it's 3.45 times 10 to the power -4. It is huge. Yeah. It's not per like 1% or 2%.
So this for forecasting, for time series forecasting.
Forecasting what is the point of a Bessel function. And this one has the less, parameter. So it performs good. For performance of continuous learning, the author also makes some results. In the first phase, they input the first one, the training, you can see the result. For out of space, you can see, both one is like this one. I mean, both perform only in their comfortable area, right? But in phase 2, we can see can perform good in both areas. However, in multi-layer perceptron, it can only come in its comfortable area. For later, they have the same issue. So, can is better in continuous learning. That is obvious, right? Okay. So as for future, let's first talk about what is the advantage of Kolmogorov-Arnold network. First, it uses less data, and then it can make a more accuracy. Now it is say it is they already have some result in low dimension. As for really high dimension, now there's no some experiment. So theoretically it's better, but there's no, experiment to prove it. That is one thing. Another thing is, it can, a great symbolic solver and interpret, it can be interpretable. Yes. And another is it solves the catastrophic forgetting, like this one. This one, multi-layer perceptron meet the catastrophic forgetting, but don't feel look at this problem. And also, we can provide both internal and external degree of freedom, which make it more accessible than MLPS, right? Multiple layer perceptron.
Okay.
So now there's still some challenge. That is, the first one is until now, we don't know how to run it in batch computation, because now, yes, and also the author also mentioned, now there's no graphics supported. Theoretically, there should be, but at least this is primitive, nobody can do it. Another issue is how this one connect to our engineering. I mean, the perfect solution would be you make this one combined with the multi-layer perceptron, or you make this one replace the multi-layer perceptron. Which one is better in which case? When we use the multi-layer perceptron and when we use Kolmogorov-Arnold network. That is another issue to be for the future. Yeah, that is all of what I want to discuss. Any questions?
I have a question about the learning process. Because in the multi-layer perceptron, we have the back propagation and using gradient descent. In this, how the iterative process works here? No answer. Yeah, this one is still in primitive field because this paper just released last month. Now it's July, should be 2 months earlier. So as for how do we learn, how it learns, it's still under investigation. Yeah, but I can show you guys some example of this one. Now they have some result for this. Let me stop sharing. Yeah, can you see my screen? Yeah. Now, I see, some they use the SPACY, that is the optimization tool to, to optimize it. They get some good results. As for the future, how do we train it? I think that is a good problem we are going to solve. First, what we first determine the control point. For this one, what they only do is the combination of different, the different functions. I mean, the different sections, so how much it will represent, what is the percentage. And then what they do is they will select the keynote vector, that is, we mentioned what is the vector represent. And then what we do is we first construct the spline basic function. And then after they construct it, what they do is they are trying to fit the target function. That is this one. How do they do it? That is how do they do it? For each time, what they are taking is from basic function and the control point. From them, you take off them and then use the b times c b the function times the CP. So now we have to guess what is the b and what is the CP. If we get it, the combination will give us a good result, right? So that comes to how do we get it? They use the species optimized. They use the least square. That is, what they are trying to get. And the result is the residual. That is what you approximate minus the real value. That is define your error. And then they use the least square. They try to minimize it by the least square and the residual. Use the residual function. That is what is your result. And what they are doing is the argument is the basic function, and you have x and y, and then you have the control point, and then you got all of the x. And based on this one, you just generate the result.
That is all of the points you get, and then you plot it out. You can see this is the base function that they generated, and then this is the curve. This is the blue one is the target line, and the right dot line is the approximation. This is perfectly follows.
Yeah, it fits.
Yeah. But the thing is, first let's say this has its advantage. What is the advantage? The advantage is for this one we don't have too many layers. We save a lot of space. I mean memory space, and also solving this issue don't cost too much. But what is the problem here now is it's not that convincing because you simply just fit a target function that is easy target function. What if the target function is more difficult? Because in practical, target function is always difficult. So how do you fit the more difficult one? The author didn't release the code for like the better one. I think they are still do some improvement. So at least for that one, we can only say is they leave the number. What is the error compared with the multi-layer perceptron? Yeah. So
for the control points in the code, we need to specify. Yeah, this one control points.
This is the index of a control point. You can see it's from 0 to 4. Yeah. And then they evenly distributed from the space. You can see that that's why they use the NP line space. They evenly distributed.
Because if you get back to the comparison with the MLP table,
Sorry?
the paper.
Paper?
Yeah.
You want to have a look on the table, right?
Yeah, the comparison with the MLP.
You want to this one?
So the KAN shape here is related to the control point?
No, the KN shape is because we need a multiple one layer. This is the one layer, right?
Yeah.
Maybe we have multiple layer. This is the first layer. Then we have another layer. During this layer, how many neurons we have? How many the functions we have here? Yeah, that is we have here. Yes. So that's it.
Can you go to the conclusion?
Sure.
I have a question. About pruning and specification and point.
Yeah.
Can you explain more about this pruning? Symbolic regression.
This okay. Yeah, I got your question. Pruning, because we can still come back to this one. Before we have a lot of basic functions, right? Activation function, and then after we training, see this one their importance is 0. That means it's gone. So it helps the neural network become sparse. That is during this process we can say it's pruning because the useless place. We just remove it.
We do it for the neural network.
Yeah. No. For neural network, what we do is drop out, but it's randomly, right?
Yeah, it depends.
Yeah.
We have the threshold. We have threshold of weights, for example, and you make it 0.
Yeah.
This is the pruning.
Yes, but for here, definitely we know which to pruning and how to pruning to increase it. No, not how to prune, but which one should be pruning and what is the rest and which variable is really related to my outcome. Which variable doesn't matter, but in neural network we cannot do that. Yeah. So that is that is the work. Okay.
Thank you so much.
Thank you. Yeah. Okay, let me stop sharing. Oh no, stop recording. I mean, where is the recording? Stop.